Hello. So we've been talking about design of optical receivers from the perspective of building optical sensors, and so far we started looking at the front end of the optical receiver, which is the photodiode, and we looked at the properties of PIN photodiode, and during the last lecture we started talking about avalanche photodiodes. We looked at how avalanche photodiode works. It's based on this impact ionization process, and then we came to the point where we were defining the multiplicative gain as a function of the bias voltage that we provide to the avalanche photodiode. And one thing that we realized was that it's best that the Ka value, which corresponds to the impact ionization ratio, the impact ionization coefficient for holes divided by the impact ionization coefficient for electrons. If that Ka value, if it's away from 1, then we make sure, then it means that only one of the carrier species, whether the electrons or the holes, are participating or generating that impact ionization, and that actually provides much better gain without incurring a lot of noise. So we talked about noise very briefly, or I just mentioned about noise. We do want to go a little more into detail as to what are the kind of noise sources in the receiver, but before we go to that, we will just complete our discussion with respect to avalanche photodiodes. So essentially what we are saying is, when you are looking at the responsivity of APD, okay, that corresponds to m times the responsivity for the PIN structure. Okay. So that's the key thing to keep in mind about avalanche photodiodes. So effectively, if you say VB is 0, then your gain value is 1. So if you take an APD and you do not actually provide an external bias, then it essentially works like a pin. Okay, but beyond that, you can actually get some multiplicative gain, and through that you can improve the responsivity of the photodiode. Okay, which corresponds to the amount of photocurrent that you generate for a certain amount of optical power that's incident on the photodiode. Okay. Now that's hopefully that's clear. Now let's actually move on and try to understand what we mean by or try to quantify what we mean by having more noise as you go to higher gain values. So how do you quantify that? Well, that can be quantified by what is called the excess noise factor. You can go to a fresh page and look at that. So what we are talking about is, maybe I can just go back to my black color. Excess noise factor as far as APDs are concerned in an APD. Okay. So the excess noise factor is quantified as this term FA. There is actually an empirical relationship for that, connecting this excess noise factor to the avalanche gain, that multiplicative gain is given by m. So it's Ka multiplied by m plus 1 minus Ka multiplied by 2 minus 1 over m. So that's actually an empirical relationship that we have for the excess noise factor. So now let's look at how this works. Okay. So let's actually plot a graph of FA, the excess noise factor, as a function of m. Okay. And let's actually look at the role of Ka in terms of the excess noise factor. Now, to look at that, first of all, we can substitute different values of Ka and see how this expression works out. So, the easiest thing is if Ka equals to 1, right. So, what happens? Well, if Ka equals to 1, then the second term disappears and you are just left with that first term. So, this is basically Fa is Ka multiplied by m. Okay. By the way, if you are wondering where all this is coming from, these are all stuff that we taught in Introduction to Photonics, but if you just want to go back and look at a text, there are several excellent texts that talk about PIN, APD, photodiode, as well as the laser sources and that we talked about previously. Saleh and Taish is one very good reference, but most of the notations that I am following is actually from this book by G.P. Agrawal, okay, which is on fiber optic communication systems. So, if you want to go back and look at that, you can follow that book. Okay. So, let us look at the case of Ka equals to 1. If we were to draw that, that's just basically a linear relationship, right. So, with a slope of 1, right. So, it's just a straight line. Okay. So, what does that tell you? Well, that tells you that whatever gain you are having from your APD, you have a corresponding noise that's coming into the picture as well. So, when you look at the signal to noise ratio, you may not be gaining much as far as this Ka equal to 1 value is concerned. Okay. Now, let us actually look at the other extreme. What if Ka equals to 0? Well, if Ka equals to 0, Fa becomes, the first term essentially vanishes and the second term Ka is 1. So, Fa is 2 minus 1 over m. So, how do we actually represent that? Let us say Fa equals to 2, that corresponds to this line here. So, 2 minus 1 over m is a function that is going to be asymptotic with respect to 2. So, it is going to be something like this. Okay. So, what does that tell us? Well, it says that whatever could be the value of m, you are going to cap your noise, that is the competition between the noise due to competition between two carriers, two different types of carriers, initiating the avalanche process, right. So, that noise is capped. That noise is capped at a value of 2. So, you can keep increasing the gain and you won't incur any extra noise than this factor of 2. So, that means that you can get whatever signal to noise ratio you want. Okay. Well, that is an hypothetical case because there is no material with Ka equal to 0. So, for example, if we consider silicon has got a Ka of 0.1. So, let us actually look at how Ka of 0.1 would look like. Well, that would be closer to 1 for low values of m, but as you go to higher values of m, it is going to start being parallel to this other line. The other line is Ka equal to 1, and here we are talking about Ka equal to 0.1, which is the case for silicon. Okay. And let us just make sure this label is also there. So, this is K equal to 0. Okay. So, what it says is that it behaves like an ideal K equal to 0 type of thing for low values of m. So, that is very good, but beyond a certain point, as you increase m, you are starting to also scale up in Fa. Essentially, this term, the first term, starts dominating beyond a certain value of m. For lower values of m, this term is dominating. For higher values of m, this term is dominating. And when you go to this regime where this term is dominating, then you lose all the benefits of using your APD. Okay. So that is to tell that, okay, if you want to use an APD, you probably want to use it up to this point, this value of m, beyond which there's really no point. Okay. So just to complete the picture, let's actually look at Ka equal to 0.5, and that again is going to look similar to this case of Ka equal to 0.1 at low values, but then as you increase further, it's going to start becoming behaving like Ka equal to 1 case at higher values of m. So here the optimum value may be something around here, which is in the order of 10, whereas here this is in the order of 100. Okay. So you can, so let's actually write it out. So for if you talk about silicon, for silicon, Ka equal to 0.1, right, and what we find is this the gain, the multiplicative gain until which you can improve your signal to noise ratio, or the multiplicative gain beyond which the signal to noise ratio is not improving, or it's only going to start degrading, is what you call as the optimum gain. Okay. So this for K equal to 0.1, the optimum gain value could be in the order of 100 to 200. Okay. In contrast, for indium gallium arsenide, Ka equal to 0.5, we are tracking this curve over here, and what that tells you is that the M-opt is going to be more in the order of 10 to 20. Okay. So you clearly with indium gallium arsenide, you would clearly have you're not going to be able to use an APD with much higher values than these. Okay. There are some specific conditions under which you could possibly push this slightly, like cooling the diode and all that. I will tell you a little later as to why that makes sense, but you could possibly improve the optimum value for indium gallium arsenide to maybe 30 or 40 by cooling the diode. Okay. We'll come back to that later. Okay. So that is actually the the some of the properties of this avalanche photodiode. Okay. Now let's look at another aspect of this, which is basically the response time of avalanche photodiodes. In a PIN photodiode, we said the response time is limited by the transit time of the carriers within this PIN structure, right. So we said F3 dB in that case is equal to let's just write it down, F3 dB for a PIN, we said it could be 1 over 2 pi tau TR, okay, where tau TR corresponds to the transit time of the carriers. Now if we do the same thing for an APD, what do you think is going to be the limiting factor? Well, of course, there is the transit time involved here, but there is going to be some additional factor that determines the response time, which is, if we go back and look at this picture over here, this is actually a sequential picture by which we are getting gain, from here to here, and then after this has happened, then this happens, and then from here you might have even more electron hole pairs generated. So that's the multiplicative gain process that we are talking about, right? So that multiplicative gain is going to take time, right? So it's going to take a finite amount of time to go through that cascade, to go through that avalanche. So effectively, when you look at the F3 dB of an APD, I am not deriving this in the interest of time, but you can go back and look at the text that I mentioned. You will find this dealt with in a little more detail, but it corresponds to 1 over 2 pi multiplied by this value of m, and I would actually denote it as m naught. So what do I mean by m naught? M naught is basically the gain at 0 frequency, at DC. Okay, so that actually is what we are denoting here. That's the multiplicative gain multiplied by some time constant, and that time constant you can call it as tau e, is the effective time constant. And turns out this effective time constant is actually given by, or it can be approximated as Ka multiplied by tau Tr. Okay. So Ka, like we said, it can be a value of 0.5 for indium gallium arsenide, 0.1 for silicon, and correspondingly, when you look at the gain value, also the gain value could be in the order of 10 for indium gallium arsenide, it could be in the order of 100 for silicon. But this is the trade-off now. What we are talking about here, because of this, what we are saying is higher gain, or you can just say that corresponds to higher responsivity, right? That implies you have lower bandwidth. Slower response time, you can call that, right? So higher gain corresponds to lower bandwidth, or in other words, if you want to achieve higher bandwidth, you will have to do that with the at the expense of dealing with lower gain value. So essentially, how do you control the gain value? Well, in a APD, we saw that we control it using your bias voltage. So if you want to have high gain, you increase your bias voltage up to so that the gain value goes to close to the optimum gain value. On the other hand, and that point the bandwidth is lower, but if you want to actually have better bandwidth, you scale down your voltage so that you can work with lower gain value. Okay, so that's actually a classic trade-off that you have as far as avalanche photodiodes are concerned. Okay, so that is something that's very important to keep in mind. Now the other question could be, when do we choose an APD, as opposed to choosing a PIN? Because PIN, we know it's a simpler structure, it's got all these properties that is very well defined. There may not be as much noise, the excess noise factor that we saw, that doesn't come into the picture as far as PIN is concerned, so that may be better for certain applications. So then the question is, when do we choose APD? We choose APD when we can afford to improve or to improve the signal. And what do we mean by this word afford? So, what we are talking about is without degrading the signal to noise ratio. Now, of course, we have not talked about noise very much, right. So, that is something that we will go into a little more detail shortly. But before we talk about this, what do we mean by this? Essentially, the without degrading signal to noise ratio means that the APD noise, the excess noise provided by the APD is lower compared to other noise sources. Okay. So, if you have the noise due to APD being lower compared to other noise sources, that is when you actually that is when you can afford to boost up the signal, and that is when you want to use an APD. Okay. So, we will look at some specific conditions related to this, but to understand this point a little more, we need to understand noise in the receiver, and to understand noise in the receiver, you need to now understand how you are basically starting with a photodiode, starting with some optical power, and how are we converting that to a voltage. So, we need to understand the receiver construction beyond the photodiode. Okay. So, that is what we will look at next.